So far we have seen John's theorem, its proof, and some corollaries related to John's theorem. Now we'll see an application of John's theorem, which is the problem called optimal design. So this is a fundamental problem in statistics, and the idea is that for a lot of statistical problems, the goal is to design efficient estimators. So estimators, for example, are basically so you want to uh, find a way to figure out what some unknown quantity is by taking measurements of that quantity, and those measurements can be noisy. So you want to take the measurement in a way that gives you the best estimate of the unknown quantity with as little samples as possible. And this area is like a very rich area of study, and there's lots of work, lots of application all over, uh, like areas like machine learning, artificial intelligence, statistics, applied math. So this is indeed quite a very interesting area. And so I want to show you how to take this John's theorem and use this in the area of optimal design to derive some efficient estimators. So let's start with this problem of the linear regression problem. I think it's familiar to a lot of people. So we are given a point set x1 to some x capital N, and this point set is in Rn as usual, right? So there are n vectors, capital N vectors given to you, and there is some theta star in Rn which is unknown, right? So our job is to, so as an observer, I can do the following. I can pick Z belongs to P, then query Z, receive Y equals to Z inner product theta star plus eta, where eta is some IIT noise. IIT noise means 0, right? So we observe only this, and our job goal is to find theta star as well as possible, right? And given budget T. So what is this budget? Budget is basically the number of times you can do this process. That pick a Z, query that point, and receive the signal. So the number of times you can do this is capital T, and you have to figure out a way to query some T points from this given set of points P such that your estimator is as good as possible. And what do you mean by as good as possible? So I'll define that in a minute. So let's uh, first start by writing out a very basic estimator that people use, and it's a very popular estimator, and this is nothing but the least square estimator. It says that minimize over all theta the sum of square loss. This is given by dt plus star, sorry, zt of theta minus yt. So here yt is the corresponding output that you received for zt theta star plus eta. And the thing is that like you query the points z1, z2 up to z capital T. So these are your query set. And of course, this is a subset of V. Actually, it doesn't have to be a set, it can be like a collection, as in querying the same point many times is allowed. So if this is defined as our estimator, then it's easy to see that with the help of this definition of V, call this T equals to 1 to T, Gt, Gt transpose. So if you define V this way, then this theta star has a uh, closed form solution, which is given by V inverse of summation T equals to 1 to T Yt Zt. And how do you get this closed form? Basically, take a derivative. It's an unconstrained minimization problem. Take a derivative, set that to 0, and like solve the linear equation that we end up getting. We get this nice form. And if we further use the fact that Yt equals to Zt inner product, Zt inner product theta star plus eta t. Let me just use eta t to denote the noise at the tth point. And they are IID, so it's fine. So if you use this, if you substitute Yt here and simplify further, what we will end up getting is theta star plus V inverse summation T equals to 1 to T eta T times Zt. So first thing to note here is that expectation of theta hat is theta star plus V inverse T equals to 1 to T expectation of eta T times Zt. And this eta T's are, as I said, mean zero noises. So this means that this is theta star. Basically, this is zero. Right. So this theta hat is indeed an unbiased estimator of theta star. But what we are interested is in a bit more. So what we want to guarantee is that, so if we use theta star to reason about an estimate of the quantity x theta star, right? X belongs to P. So this is the quantity we care about. So we want to say that what is the deviation, or what is the uh, what is the actual deviation between x theta star and x theta hat. So we want to minimize this quantity in some sense. So what we want is, more specifically, we want the expected, basically let's just call this the variance. We want the variance of this thing to be small. And why do we care about this? Because, I mean, if the variance is small, this means that the estimate is good at every point of P, right? And that is what we essentially want. We don't just want an unbiased estimator which says that if you have infinite samples, then indeed theta hat will be exactly theta star. But we also want to reason about what happens in the finite sample regime, right? So they're using variance, like how much this quantity can vary, is a good way to capture the idea that we want that this estimate of x theta star is close to x uh, is close to the true value. So what happens to this variance? So note that x theta hat minus x theta star. This is a mean zero random variable, right? Because expectation of theta hat is exactly theta star. So the expectation of this quantity is nothing but x. But this is by linearity of expectation. right? This is x comma 0. So therefore, the variance of this quantity is nothing but expectation of x of theta hat minus theta star square, right? And now let's try to see what this is. So again, using this fact that theta star, theta hat is theta star plus this quantity, we will have theta hat minus theta star is actually this quantity. So here, what we can replace is this is V inverse summation t equals to 1 to t theta t ct square. Fine. So this is again can be written as this is summation t equals to 1 to t theta t times x v inverse ct. I just pulled the summation outside, right? And you still have the square hanging out. And now note that these eta t's are IIT, right? So we know that, and eta t IIT and mean 0. So what happens to an expectation of such mean 0 IIT random variables? So if you have a lot of xi square, right, I equals to 1 to some n, where xi are IIT mean 0, then this thing is exactly equals to summation I equals to 1 to n expectation of xi square, and which is again equals to I equals to 1 to n variance of xi. And since they are IIT, we get n times variance of xi. Yeah, x. So essentially, this quantity will become summation t equals to 1 to t eta t. Sorry. So yeah, variance of eta t times x v inverse ct, and this is nothing but t equals to 1 to t x v inverse zt whole square times variance of eta t, and say variance of eta t is some constant, right? For example, if it's a Gaussian, then this is sigma square. This is the sigma square times t equals to 1 to t x comma v inverse zt whole square. Writing it the other way, you can see that this is sigma square t x v inverse zt. So if I write it in the transpose form, then what we have is x transpose v inverse zt times gt transpose v inverse x. Note that v is symmetric. So you can break the square into two parts and take a transpose inside. This works out. So this is sigma square. Now zt's are the only things being summed over. So this is x transpose v inverse t zt transpose times v inverse x. And this is equals to v. So one v inverse and one v cancels out. What you have is sigma square x transpose v inverse x. So essentially what we have shown is that the variance of the quantity x theta hat minus theta star is equals to sigma square, which is the variance of the noise, times x transpose v inverse x. And this is for all x in P. In fact, for any x So what we desire is that we want to minimize this quantity, this variance over all x in P. So we want minimize x transpose V inverse x for all x in P. And the better way of saying this is minimize over the choice of Z1, Z2, Zt, maximum of x belongs to P, x transpose V inverse x. So this problem is actually the optimal design in the sense that it's saying that find me a collection of query points such that when I estimate theta from this query points, the estimated that I get is a has nice properties in terms of variance of the estimates for the point set. And note that the number of things in this point set can be much larger than P. There are endpoints in the point set, and that can be very large. So it's not possible to query every point sufficient number of times to bound this variance. So we have to do something more clever. But before that, like what we can do, let's do a relaxation of this problem in the following sense. So here, this Z1 to ZT, these are being picked as like these are this is sort of an integer programming, right? So you want to decide how many times to query each of the xi's belongs to P. And if, for example, say x1 has to be queried 10 times, so you can pick z1, z2 up to z10, all of them equals to x1. And thereafter you can like pick the next set of points. So this way, this is basically an integer programming problem. And I mean, the general belief is that these problems are hard computationally. So we do a relaxation. We say that give me a distribution over P such that the maximum for all x in P, x transpose V inverse x is minimized, where I'll define what distribution over P is. This is basically collection of all lambda belongs to Rn. Actually, keep it to be 0, 1 power n such that summation lambda I equals to 1 to n equals to 1. So basically, this is the probability with which you will sample every point in P. And now the definition of V basically becomes the expected design matrix. So this is I equals to 1 to n lambda I xi transpose. So with these two definitions, we want to solve this problem. And this problem is called the G-optimal design. Our goal will be to see how to solve this problem. And you can see that this is a non-convex problem. So, I mean, how to solve this is not clear upfront, but we will see that you can actually get away with solving some other convex problem whose solution happens to match the solution of the G-optimal design. And that is called the Kiefer-Ulfowitz equivalence theorem. So we will see what that is and how to arrive at that problem in the next video.